All right, happy Monday. This is lecture 13. We're continuing section 7.6, applications of integration. Comes up in these problems sometimes things involving, well, it comes up a lot, units. So distance, mass, force, energy, and acceleration of gravity. So you're stuck with, unfortunately, having to deal with both English and metric system units. So what's the standard metric system unit for length? Marcy?
Meter.
Okay. What's the standard metric unit, the English unit distance? So this is meter, and we use a small m. What about for English? What's the standard unit of length? Okay. Feet, which is abbreviated FT. Okay, somebody else. What's the standard unit of mass in the metric system? Jace?
Grams.
Yeah. Yeah.
Kilogram.
Yeah, so gram is sort of more fundamental. Kilogram is 1,000 grams, but actually kilogram is what's most often used. So it's kind of dorky. The standard is 1,000 of some other thing, so kilogram. What's the standard unit of mass in the English system? No, that's unit of force. What's the unit of force? Yeah.
The unit of mass in English?
Mm-hmm.
Slugs?
Yes. How do you know that?
I spent a large portion of my life around scientists.
All right. What's the standard unit of force in the metric system? Yeah.
Newton?
Yeah. Okay. So I'm not going to call on repeat customers here, so I need some new hands here. What's the standard unit of energy in the metric system? Yeah.
Joules?
Yeah, and how is that? What? We'll come to that in a minute. The joule, abbreviated J. What's the standard unit of energy in the English system? William? Say it again? Yeah, I guess it is. Yeah, no, right, yeah. So it's actually, so go back to this. A joule is one Newton times 1 meter. So if you are pushing on something with a force of 1 Newton and you move it 1 meter, you've done 1 joule of work. So the unit of energy or work, we're going to be using foot times pounds. So yeah, British thermal units, BTUs, that is a unit of energy, but we're going to be using just our unit of force times our unit of distance to get a unit of energy. What's the acceleration of gravity in the metric system? I'm not going to be calling on repeat customers here. I'm going to need some new hands up. What is G? you're shy about answering, you should answer early on when the questions are easier, because the questions just get harder. What is G? Ethan, your hand is kind of up.
Is it meters per second?
No, that's the unit of speed. That's the unit of velocity. This is the acceleration of gravity. It's come up already in this class. Yeah.
Meters per second squared.
That's the unit of it, but what's the value? The particular.
9.81.
Yeah. 9.81 meters per second squared, or 9.8 roughly. What's the acceleration of gravity in the English system? Anybody remember?
32.
Say it again?
32.
Well, it's going to be whatever our unit of distance is, feet, divided by our standard unit of time, seconds squared. So there we go. Now, notice that well, anybody ever lift weights? Yeah, okay. So what if what if there's a disc in the weight room that's labeled 100 kilograms? What does that weigh? Marcy?
980 newtons.
Say it again?
980 newtons.
Right. So the weight is whatever the mass is times the acceleration of gravity. So for a 100 kilogram mass, if there's a disc in the weight room that's labeled 100 kilograms, that's not the weight, that's the mass. The weight would be 100 kilograms. Wait a second. It's kilograms times g, 9.8 meters per second squared. What's up with that? Yeah.
Because the weight of anything is just the mass times the acceleration due to gravity.
Well, I already did that. But what's up with this kilogram meters per second squared thing?
That's what a newton is.
That's what a newton is. So 980 kilogram meters per second squared. That's what a newton is. 980 newtons. So that disc in the weight room doesn't weigh 100 kilograms. It weighs 980 newtons. If you're talking kilograms, it's you're talking about a unit of mass. How much does that 100 kilogram disc weigh in pounds? It's about 225 pounds, 100 kilogram mass. How many slugs of mass are in that 100 kilogram? I don't know. But observe that the acceleration of gravity is 9.8 meters per second squared. But I can do a trick. This is 9.8. I'm going to put kilograms on top. And then I'm going to divide by kilograms. Just multiply and divide by kilograms. Why would I want to do that? Well, because that's 9.8 newtons per kilogram. So that's actually a handy thing for G. Instead of thinking of G as an acceleration, meters per second squared, that's meters per second per second. That's how fast something is accelerating when it's under the influence of gravity. Or you can think of the constant G as how many newtons per kilogram of mass do you have? So if you have 100 kilogram mass, you've got 980 newtons of force on that. All right, that's going to come up. Now, having said all this, you'll find sloppy stuff, like in our book. It'll talk about something that weighs a certain number of kilograms. That's just dumb. It's just simply not right. Something doesn't weigh kilograms. It has a unit of mass that's kilograms. So you have to, you want to get the language right, because if we're going to be talking about work, which is force times distance, and so you want to be sure that you're dealing with units of force, not with units of mass. Okay. So all these things will come up. Oh, another thing that will come up today, density. So the symbol for density is rho, R-H-O, the Greek letter. So the density of water. Anybody remember this? Cassie, you sort of had your hand up. Yeah.
It's pretty close to one.
One what, though?
Or something, I can't remember.
Yeah.
Gram per cubic centimeter.
Exactly. Yeah. It's not pretty close to it. It's exactly 1 gram per cc. So in fact, if you look at your measuring cup in the kitchen, it's got cups, it's got English units on one side, cups and ounces. On the other side, it's got milliliters. But that's also, a milliliter is a cc. And so if you fill that thing up to, a liter of water, that's 1,000 cc's of water, has a mass of 1,000 grams. So that's one thing that I can remember. Anybody remember this? Anybody know the slogan for the mass or weight of water in the English system? Okay, repeat after me. Ready? A pint's a pound the world. A pint's a pound the world around. Ready?
A pint's a pound the world around.
All right. So a pint of water weighs a pound. I don't know what the mass is because it's the damn slugs thing. But if you fill up your measuring cup with a pint of water, that's a pound. That's 16 ounces. So in fact, when you look at your measuring cup, it's got ounces listed. Well, are they fluid ounces or are they units of weight? Same thing. 16 ounces of water has a weight of 16 ounces or 1 pound. So that's kind of a goofy thing. Okay, now let's think about this. This is 1 gram, and now a cc is 1/100th of a meter. And so a cubic centimeter is that cubed. Again, a centimeter is 100th of a meter, and we're going to cube that, so that's 1/100 cube. And so that's, well, I can flip this over and multiply, so I have 100 cubed, and then I have grams per meter cubed. Now 100 cubed, that's 10 to the 6th. One million grams per cubic meter. Here's where kilograms would come in handy. How many kilograms is this? Jace? 1,000, because a kilo means 1,000. So this is 1,000 thousands. So this is 1,000 kilograms per meter cubed. That's the density of water. That's going to be handy. That's quoted in the book. But for the life of me, I would not bet anything on remembering this beyond today. I have the memory of a goldfish. But the damn cc thing, the cc of water weighs a gram, or it has a mass of a gram. That I can remember. So from that, you can get to everything. All right, so today we're going to just be doing some problems involving work. Again, just continuation of the subject from Friday. So example 1. Now, a common gripe among students is classes where you don't get to use calculators. The thing about that is, if I have a class where we're using calculators on quizzes or exams, the problems are a lot harder. I make problems that are hard, because if I know you're going to be using a calculator, I ask harder questions. If we're not using calculators, I ask problems in a way that you don't need a calculator. But even if you have a calculator, there's a way of using calculators that I think is wiser, in which you don't use the calculator throughout the solution of the problem. You use the calculator at the very end. So even if you have a calculator, I don't suggest that you get it out until you're ready at the very end of a problem. So I'm going to be solving problems here. On your homework, you have a lot of homework problems where you have to type in a number. You have to type in a decimal approximation. And my recommendation is you don't do what they do in the book. In the book, they solve problems and they've got decimal numbers appearing throughout their solutions. And then you think, well, how the hell would I do this if I didn't have a calculator? I couldn't do any of this. If every step I'm typing something into a calculator, then you're not training yourself for any situation where you don't have a calculator. So what I'm going to be doing today is what I would urge you to do. Even if you have a calculator, use it in a smart way so that it comes at the very end of the problem. So here we go. A heavy cable has mass per length of 1/2 kilogram per meter. Now, mass per length is often given a letter, lambda. This is the Greek letter lambda. It dangles off of a tall building. Mass per length, lambda, and length, capital L, equals 30 meters. Dangles from a pulley that's attached to the corner of a tall building. So attached to the edge of the roof of a tall building. So here's my situation. I've got this tall building, I've got a pulley here, and I've got dangling from this pulley this cable. I'm going to color my cable yellow. The question is, how much work is required to spool that cable onto that pulley? In other words, to lift all this cable up and get it around that pulley. So how much work was required to spool the cable onto the pulley? Now, we're assuming this is a really expensive pulley that, there's no friction or anything, so the only work is required is the work for lifting that cable. Well, one thing that I think is very important in problems like this is that you establish a coordinate axis right away, a direction for the axis and just 0 for the axis. So we're going to establish a y-axis. Got to say which way it's pointing up. And with the origin at where the cable bottom was originally located. So at the original bottom location of the cable. So I add that to my drawing. Here's my y-axis. It's pointing up, and its original location is there. Its 0 is there where the cable is originally hanging. But of course, this cable can get spooled up, and could be here. So this distance is the original length L. Capital L is the distance from the top of the building to there. So this point up here would be y equals capital L. And then the current location of the bottom of the cable is just going to be y. So the current location of the bottom of the cable is y. So y is going to be a number that's greater than or equal to 0 and less than or equal to L. So if the cable is,
Mr. Barsamian,
yeah,
the original length thing should be smaller to fit the length of the verb.
no, this is, so here the cable has been spooled up. So I've got some cable
Oh, okay.
been spooled up here.
Are we just making like one fold rotation, or?
So the cable can look like this, it can look like this. As I spool the cable up, so y is a variable thing. So if y is 0, that means the cable is all the way unspooled. If y is L, that means the cable has been spooled all the way up and is all the way on the spool. Okay, so the mass of the cable So here's where I'm going to talk about, numbers, not using calculators. In fact, I'm going to talk about not even using numbers. When I say the current, I mean like while the cable's being lifted at some point in time. The current mass is going to be whatever the current length is times the cable density per unit length. Now that number lambda is 1/2 kilograms per meter, but there's no reason to put those numbers in units in there right now. Just use the symbol lambda for the density for the mass per length. And so what's the current weight of the cable? Ian?
Would it be lambda times y times g?
Exactly. Lambda times g times y. Again, g is the number 9.8 newtons per kilogram, but there's no reason to put that number in there. Just use the letter g. Work with g. So that's how much force is required. So when the cable is dangling off that pulley, and whether or not it's fully extended or not, however much cable is there, if the position of the cable is y, then that's the force that is required to hold that cable up. Now in these problems, we have this kind of simplistic idea that that's the force required to hold the cable in place, or to, if you move something with constant speed, if you're not accelerating it, then that's also the force to move this. You would still be holding it with that same force. If you've got this cable and you're pulling it up at a constant speed, that would be the force that you'd be holding that cable with. Now notice that changes as the cable length changes. So this is the force as a function of y. So notice when the cable is fully unspooled, that's not right, is it?
Is your y the distance from the initial
Right,
spot
so what-
to where it now is the bottom?
What I need to have here is the length of the cable. Let me go back up here. Current length of the cable is L minus y. So if length is going to be between 0 and L. So in other words, when y is 0, the length of the cable is actually L, and when y is L, the length of the cable is 0. So the mass of the cable is lambda times L minus y. And then the force, the weight of the cable is going to be lambda g times L minus y. And so the distance that and so I'm changing the way I want to do this. I don't like my solution.
Isn't your force still a function of y by itself because it's how much it's gone? How much
Yeah.
it's traveled? So it would still just be lambda g times y.
Yeah, I'm going to do this a different way. The book does these a little bit differently, and I'm going to maybe change. Sorry about this. I just realized maybe I like the way the book does this a little bit better. So imagine a little piece of the cable of length dy. So I've got this little piece of the cable. Of length dy. And it's located at y. Okay, so the mass of that piece of cable would be lambda dy. And so its weight would be lambda times g dy. Now the distance that that little piece of cable has to be lifted is, well, whatever y is, we have to get up to L. So the distance it must be lifted is capital D would be L minus y. So that's this distance here. And so the work to get that little piece of cable up to this pulley would be, well, that force times that distance. So lambda g times the quantity L minus y dy. So that's the work to just get one little piece of this cable onto the pulley. Now I've got to add up all the different lengths for the whole pulley, or for the whole rope, or whole cable. So that's going to be capital W, and that's going to be the integral as y goes from 0 to L of that quantity. So lambda g times L minus y dy. So let's bring the lambda and the g out. Integral from 0 to L of L minus y dy. Now, L is a constant, y is a variable. So when I integrate this, I get lambda g times Ly minus y squared over 2, evaluated from y equals 0 to y equals L. Well, let's keep going. Well, when I plug in 0, this whole thing goes away, so I really just need to plug in L. So lambda g times the quantity L times L minus L squared over 2. Oh, but that's just L squared minus L squared over 2. So I just get work equals lambda g L squared over 2. So notice I've gone this whole way without using a calculator. Even if I had a calculator, which I do, and when I do my work, I'm sitting at my desk with a computer that calculates stuff. But this is the way I do my problems. I don't plug numbers in. And now let's use the numbers. Well, let's see. My lambda is 1/2 kilogram per meter. You plug in the numbers with the units. This is another thing I want to stress. Our book doesn't do this. Our book just does calculations involving numbers, and at the end they slap on units. But it's important to learn how to do calculations with numbers and units. And there's an algebra of numbers going on, and there's an algebra of units, or arithmetic of numbers and an arithmetic of units. And you have these two kind of parallel worlds going on. So there's my lambda. My G is 9.8 newtons per kilogram. My L is, what did I say, 30 meters squared.
It's just 3 meters, right?
Oh, that should have said 30. I wouldn't want to have a cable that short. I'd feel cheated. Let's use 30. Because it's a tall building, where it's like a paint bucket or something. And then there's another 2. So look, we've got, again, an arithmetic of numbers going on here. We're going to have 9.8 times 30 squared. Now that I can do in my head. That's 900. So 9.8 times 900 divided by 4. And then what else have I got? I've got, notice I've got kilograms on top that cancel my kilograms on bottom. And then I've got meters squared on top, but I've got meter on bottom. So those cancel, so I end up with Newton meters. Oh, but that's joules. So there's my number. Now, if you're curious to know what that number is, you can type it into a calculator. But like on a quiz or exam, boom, you're done. You don't need the number. But again, even if you're at home and you have a calculator, this is where you get the calculator out and you do a computation. You don't do calculations along the way. Because for one thing, at the very end, you want to check that your units have worked out. Okay, example 2, I'm going to leave that whole thing up. Nah, example 2. Same cable, but holding a 50 kilogram bucket. So now how much work? To lift the cable and the bucket.
The whole way?
Say it again?
The whole way?
Yeah, all the way up. Well, clearly we already know how much work it takes to lift the cable. That's not going to change. So there's going to be two components. The work of the cable, which we've already done, plus the work to lift the bucket. Well, the work to lift the cable is lambda g L squared over 2. What about the bucket? What's the mass of the bucket? Yeah.
50 kilograms.
Exactly. So whatever the mass is, capital M. So I should say capital M equals 50 kilogram bucket. What's the weight of the bucket? You scratched your nose. Does that mean you know? What if the bucket has a mass of 50 kilograms? What's its weight? William? I mean, Ian?
50 times 9.8.
Yeah, no, yeah, exactly. So 50 times G, whatever G is. And then that's a constant force. So how much work does it take to get that bucket to the roof? What's the distance it has to be lifted through? It was originally dangling from the cable. The cable was originally length L. And so this bucket with a certain mass gets moved from y equals 0 to y equals capital L. So the distance it moves is there, L. So mass times g is force. Force times distance is work. When you have a constant force, you don't have to integrate. So there we go. There's our answer. And if I want to, I could plug in my numbers. So I get 9.8 times 900 over 4 joules. And over here I have 50 times 9.8. 50 kilograms times 9.8 newtons per kilogram times 30 meters. So let's check the numbers. Oh, the units. Kilograms cancel kilograms. I end up with Newton meters. That's joules. So I end up with 50 times 9.8. So over here I had joules. So I end up with 50 times 9.8 times 30 joules. So that whole thing is the number of joules. So again, if you want a decimal, here's the point where you get your calculator out. You don't do the calculators before. And again, I wouldn't even put numbers in till the very end. Work with letters, because you begin to. Once you plug in numbers, it looks like no problem ever, except just that one problem. But if you work with letters, then you start to see these patterns, and you start to see things again. You realize, oh yeah, I've done the same calculation before. The numbers are different, but the letters are the same. All right. Example 3. So that was I should have said earlier in the hour when I started that example with the cable, I should have said part 2, which is lifting heavy cables. So part 3 of the meeting is pumping liquid out of tanks. Okay, so an inverted cone has radius capital RC equals 5 meters. It has height HC of 7 meters. And it's filled with water to a depth of 6 meters. But I'm going to give that a name. HW equals 6 meters. So here's the picture. So the radius of the cone is 5 meters. The height of the cone is 7 meters. And I've got water not quite to the top. So the height of the water is 6 meters. So the question is, how much work is required to pump all this water out of the cone? Now, that means you just got to get the water up to the lip of the cone. From there, it just spills out and goes away. So how much work is required to pump that water up to the level of the rim of the cone? So we have to lift the water to the rim of the cone. So that's the question. How much work is required to pump the water out? Well, as with the previous problem, we want to establish an axis, a coordinate axis. Say which way. It's pointing with origin maybe at the tip of the cone. Or at the bottom of the cone. So here's my axis. And then let's look at a disk of water here. In fact, I don't want to say disk. I want to think about a slab of water at height y and thickness dy. So a slab of water at height y with thickness dy. So we want to find out how much mass is in that slab of water. We want to find out ultimately how much that slab of water weighs. But we're going to need to know the radius of that disk. Well, luckily we can use similar triangles. So here's my cone with radius capital RC and height capital HC. And then I've got my disk that's here, and its height is Y, and its radius is R. So by similar triangles, we get that little r over capital RC equals little y over capital HC. So little r is equal to y times capital RC over capital HC. Those are numbers, but I don't care. I just want to keep the symbols. So that's the radius of the disk. So the area of the disk is going to be pi times little r squared. So that's going to be pi times y RC over HC. That whole thing's squared. But y is a variable and RC and HC are constants. So I'm going to find it useful to pull out the y. So this is going to be pi RC squared over HC squared times y squared. And so the volume of the disk is going to be, well, it's going to be the area times dy. So it's going to be all that stuff, pi RC squared over HC squared y squared dy. The mass of the disk is going to be, well, whatever the density of water is, which we know it's 1,000 kilograms per cubic meter, but we don't care about that number right now. I'm just going to use this symbol. It's going to be that density times the volume. So, and then the weight of the disk is going to be G times the mass. So I'm going to put these together. So I'm going to have a rho and a G tacked on in front of that. So I'm going to have pi times rho times G times RC squared over HC squared y squared dy. That's the force, that's the weight of that disk. So that's how much force it takes to hold that disk in place or to move it. Now, that disk has to be moved. In order to get that disk out, well, what is the distance that that disk needs to be moved in order to get it out of this cone? Say it again?
HC?
Well, that's the height of the whole cone. HC minus y. So it must be moved at distance d, which is HC minus y. So the work to move that disk is the weight of the disk times that distance. So it's going to be weight. So the work is going to be the weight times the distance. So it's going to be this whole mess, pi rho G RC squared over HC squared, pi rho G RC squared over HC squared times y squared times HC minus y dy. Now, if you look in your book, you know, every step of the way here, they would have numbers. And again, this is how I recommend you don't work. Don't work by plugging in numbers. Just work in these symbols because you don't need numbers. And so and actually I should call that dW. So the total work is I have to integrate. I have to integrate from, well, the bottom of that water is 0, and the top of the water, the highest disk, is at y equals hc. All this junk, pi rho g rc over hc. So pi rho g rc squared over hc squared, y squared times hc minus y dy. Looks terrible, but keep in mind, most of the symbols there are actually constants. So I'm going to pull those out. Pi rho g rc squared over hc squared. And I have the integral from 0 to hc. And it's helpful to have these separate. So I'm going to have y squared hc, or hc times y squared, and then just y cubed minus y cubed. I have 2 minutes to get my act together. So when I integrate this, integrate y squared, I get y cubed over 3. I integrate y cubed, I get y to the 4th over 4. So I get pi rho g rc squared over hc squared, all that mess in front. And then I have hc y cubed over 3 minus y cubed, y to the 4th over 4. But I have to evaluate from y equals 0 to y equals hc. Well, you can see when y is equal to 0, both those terms go away. So all I really need to do is plug in hc. So I get hc times hc cubed, so I'm going to have hc to the 4th. So pi rho g rc cubed, rc squared over hc squared, and then I have hc to the 4th over 3 minus hc to the 4th over 4. Look at that. Isn't that pretty? Look at all those hc's that are going to cancel. I'm going to end up with that hc squared killing 2 of those factors, and I can pull those out front. So I get pi rho g rc squared hc squared, and then I have 1/3 minus 1/4. Now what's 1/3 minus 1/4? 1/12. Isn't that pretty? Yes, it's pretty. So there's my answer in just symbols. Now I can plug in numbers. Pi rho is 1,000 kilograms. Now this is going to be the kicker. Kilograms per meter cubed. 9.8 newtons per kilogram. That's my G. RC is, was it 5 meters squared? HC, the height of the cone was, oh, bad Dobby. The bottom disk is at height 0. The top disk is at HW. The water is not the same height as the cone. So this should be, oh yeah, bad Dobby. All right, so I have, I got ahead of myself trying to fix this. So let me just get these symbols right. Y goes from 0 to H of the water. So I should have HC times HW cubed over 3 minus HW to the 4th over 4. All right, at this point we're out of time, but you can see that you can plug in numbers and you'll get, you plug in the density of water, the acceleration of gravity, the radius of the cone, the height of the cone, height of the water, and you get a number. At the very end, you plug in numbers. All right, so I'll see you Wednesday.